Okay, so I might as well start. Um, so this talk, I'm giving you talk. Obviously, I'm the PI for the Moby team. Moby is the marine optical buoy. You'll see lots of pictures that we go through there. The Moby team consists of myself, Carol Johnson at NIST, and a couple other people who worked over the years at NIST with the team. Mark Yarborough is the lead at Moss Landing Marine Lab, which is part of San Jose State University now. And so the group, they do most of the work. I'm the PI, so I just write reports. And Carol's sort of our expert on the inside. So this is an effort that's been going on for a long time, and I'll explain it as we go along. Yes. National Institute of Standards and Technology. She's at Gaithersburg, Maryland. So you've seen various versions of this. This is sort of the science paper that Clark, Ewing, and Lorenzen aircraft measurements showed that if you flew over the ocean with a radiometer, that you'd be able to distinguish the level of chlorophyll in the water. Okay, you've seen this ad nauseum by now. Everybody has their favorite picture of it. This is my favorite picture of the problem with ocean color. It looked really easy from what we saw before. But if you look at the top of the atmosphere, these are the same curves for basically high chlorophyll up here and low chlorophyll there. But you look what's going to be going on after you get to the top of the atmosphere, and you're just looking at the little difference here between high and low at the top of the atmosphere versus at the bottom of the atmosphere. It looks like that. So you've got to get distinguished between high and low chlorophyll up here. You have to have really accurate measurements and really accurate technique to get the water leaving radiance. And your accuracy has to be that your measurements have to be within 0.5% at the top of the atmosphere to get 5% at the surface. We don't know how to radiometrically calibrate something to 0.5%. And then launch it and go through that process. So the whole thing depends on something called system vicarious calibration, where after the satellite's in orbit, you get really accurate ground truth. And it's called system because you're calibrating not just the sensor, but also the atmospheric correction algorithm that's in the process. So basically, I don't know anybody who's been able to successfully launch an ocean color satellite and get good data without doing system vicarious calibration. Maris thought they would be able to do it for a while, but gave up and ended up doing this. So accurate measurements of the water leaving radiance are required to do ocean color. And hence the title of this class is Calibration, Validation, Ocean Color, Remote Sensing. That's what this whole thing is supposed to be about. So what I'm going to do in this talk is give you a short history of Moby project and its beginning, the current status of the project, and where we're going with it. Okay, and there's a whole bunch of pictures, like I say, so it's going to be a pretty light talk. Should be a light talk. Driving force for Moby came from CCTS. Basically, CCTS launched in 1978. They had these post-launch validation cruises scheduled, the Gulf of Mexico and the RV Athena. Here's a picture of the rooster tail that comes off the RV Athena. Anybody ever see the Athena? It was a converted gunboat from Vietnam. What they did to it is they put a jet engine in the middle of it effectively. And so the whole middle of the boat was taken up by this jet engine. So it could go really, really fast. It's the idea that Dennis Clark, who was leading the effort, had with that was he could, if there was cloudy here, he could go there, or he could chase underneath the satellite overpasses and try to make sure he was in a good spot. When the engine was running, it was just impossible to do anything on the boat. It was just so loud. And there's a bunch of other stories that I won't do. Anyway, so that was a 14-day cruise they had in the Gulf of Mexico on that. In Baja, they had a 22-day cruise on a regular kind of research vessel. And then they had the Athena again on the East Coast, 25 days. So 61 days of ship time. Think about how much time is involved with getting ready to go on a ship, do the ship, come off, how many people are involved with it. They had 55 stations during those 61 days because they're doing ocean color. If it's cloudy and overcast, they didn't pick the station necessarily. Only 9 of all these stations out of all these things were suitable for calibration. So it's a lot of effort to get a little bit of data, roughly. And so basically, Dennis Clark, who was leading the Athena cruise, here's Dennis. He's passed away now, but he was at NOAA. That's Mark Yarbrough, who is one of the co-authors here. This is a long time ago. Basically, he got the idea of doing an autonomous platform. And so what he wanted to find was a place where he needed a platform, let's send data back daily, so you could continuously look at the data. The requirements for the site were clear sky statistics, because that's what we're trying to do with open color, or have to do. Homogeneous waters with a clean atmosphere. You saw the atmospheric correction stuff a second ago. You don't want to have a stressed atmospheric correction algorithm. You want it as simple as you possibly can. So that's not where your problem is. You know your problem's in the calibration part. So you want a clean atmosphere, homogeneous waters, because we're working with 1 kilometer pixels. And you don't want your one measurement here not to represent a big enough thing to represent the pixel. The site would have to be logistically possible, meaning it had to be close enough to some place with ships that you could use to service the site, and a reasonable chance of low sea state. And to get the data back, you have some communication somehow. And so if you had cell phones, you could coverage, you'd be good. So Dennis began development of this system in, I didn't update this, so 36 years ago or whatever, 1985. I was at this lab then, and got there in 84, graduated. For you guys, you see these things when you have new classes every year. At the beginning of the year, they tell you your students have only known CDs, or your students have never known this or that. You guys don't realize 85 computers. That was the first Apple Mac, right? There was no laptops. Okay. Dennis had an Apple portable that he would carry around. I'd be in the lab at this lab. He'd come to visit because Roz Austin, my boss, was really a guru in this stuff. He'd come and visit, and he'd be carrying one of these Apple portables. You ever seen an Apple portable? It's about that big. It weighs about 30 pounds. He'd have it over his shoulder, have him carry it through the airport, smoking a cigarette. Anyway, so it was pretty funny when you come in. Modus through NASA started funding around 1990. Before that, what Dennis was doing in NOAA was every time they had year-end money, you buy a little piece of something that would go toward Moby. So some of the parts in Moby that we're still using were bought in that period around 1985. So Modus started funding it around 1990, so he was part of the Modus team. And then CWIFS provided accelerated funding in 91 to try to get things going quick enough so it would be in time for the CWIFS launch, which I think was in 97. The first prototype was deployed in Monterey Bay in 93, which is where Moss Landing Marine Lab is. That's why that was there. In Hawaii, they deployed a prototype in 95, and we've been collecting data operationally since 97. So the data set goes back. In 97, it's deployed now off Lanai, Hawaii. So I'll show you. Yeah, I'll show you a picture. So it's in the Hawaiian Islands. And it was funded by NASA through most of the early time. And since 2007, it's been funded by NOAA. And basically, 2 instruments have been in the field alternating over the last 20 years. We put one in, and 4 months later, switch it for another one, and bring it back, and refurbish and recalibrate. The site chosen to do it was off Lanai, Hawaii. So here's Lanai, here's the Moby site. We can get back and forth with ship. pretty easily. Here's the KOK, which has been retired and sold sort of unsuccessfully, I guess. If the people who bought it didn't really do anything with it. But anyway, so you can get from Honolulu there, fairly reasonable. University of Hawaii let us set up this big tent on their grounds. We have a lot of these vans for storage. The University of Hawaii got kicked off of this site and moved to another site, so we moved our tent and everything to their new site in Honolulu. Yeah, so all this is in Honolulu. Basically, we're using a commercial ship now because UH doesn't have a ship we can use. What Moby looks like is this. Well, here's Moby. It's attached to a mooring. We're in 1,200 meters of water. Just a lot of details on how you have to do engineer a mooring. For Moby, what it looks like is this. Down in the bottom here is where we have the optical system, the spectrometers. Keep it at the bottom because it's basically a nice temperature regime. It's not going to get change temperature too much, so it stays in a stable temperature. Down here in this container are also the batteries. We have 4 banks of big batteries, so it can power itself, that are recharged from the solar panels. There's a power junction. So the batteries are down here because they're heavy, so they act like a weight to keep us vertical. On each of these arms, there's 3 arms. In each of the arms, there's a 2 fiber optic cables that bring the light down into the spectrometer. One detector looking down and measures LU. We measure ED with a collector on the top. So each of these has an ED and an LU collector. There's an ES collector at the top. There's cell antennas, GPS, VHF, Argos. There's another thing other than Argos now. Strobes for ships to know that we're there. And the controller is up here too. So basically all the optical measurements are made down here, and fiber optics carry the light signal down from the collector. Okay? The whole thing, the depth, the measurements are 1 meter, 5 meters, and 9 meters. Depth here is about 12 meters. So it's about 14, 15 meter long. It's fairly heavy.
All the fibers go to the same spec?
All the fibers go to the same spec. I'll show you a picture of that in a second. Yeah, there you are. So this is a picture of the system as when they made one that you could deploy. So the one we're using in Moby is slightly different in that this mirror, 4-position mirror brings in, well, it's more than 4 positions. It brings in the different fibers one at a time, the light from the fibers. That light comes in, goes through a depolarizer into a dichroic water mirror, which there's 2 spectrographs in the system, one to carry the blue side, one to do the red side, to cover the whole spectrum, since the red's so much weaker than the blue, and it's clear water. There's an overlap region. 640 is where the blue one stops, 550 the red one starts, which turned out to be useful. So this dichroic water mirror sends the blue light this way and lets the red light through, and it all goes through to a on a holographic gratings, and then onto a CC array. Okay. It's hyperspectral. We have measurements every about 0.6 nanometers in the blue, and the full width at half maximum. If you remember me talking about spectrographs, you got to worry about what the real full width is. These we sample at 0.57, but the spectral resolution is really about 0.91 and 1.2 nanometers for the blue and the red spectrograph. Okay, but it is very versus 10 nanometers or something for those satellite sensors. So it is very good spectral resolution. And like anything with a hyperspectral, then we can put together different satellite systems, mock those up, including out-of-band response, and so provide calibration data for all the any ocean color sensor that they want. Needs it. It's been extensively characterized. The stray light surface is at NIST. It's basically I answered a question I think about it. It's a laser system that is set up so you pick whatever line you want, and you just work your way through the spectrum. I'll show you some data from that in a minute or a little bit later. So stray lights, characterized. We do pre and post radiometric response, directly traceable to NIST. We have a bunch of other custom instruments that are in Hawaii that monitor the sources to make sure that we're staying stable between the times when the sources go back to NIST. We have diver calibrations monthly and cleaning. I'll tell you the truth, the calibrations aren't that, we're measuring things. We want to be calibrations to 2%. It's really hard to do that on a diver. But the diver does do monthly, and we'll do the calibration. It gives us if something drastic happens, we know we can get a timing for it. We have onboard calibration sources that are monitored every day. And the area around the site was characterized pretty extensively at the early times of the project. So now we have over a 20-year, I did not say this, sorry. We have like a 20-year time series. And you can see we make measurements 3 times a day. And so this is sort of, each of the colors represents a different hour measurement. We measure noon, 10 o'clock in the morning. It's easy, Hawaii is easy to go between GMT and regular because it's 10 hours and there's no daylight savings time. So 10 o'clock in the morning, 11 o'clock in the morning, noon, and 1 o'clock in the afternoon, and this is then 2 o'clock in the afternoon. Basically, the red dotted line is a fit to all the data going on, and there's almost no trend over the 20. At this point, it's a 19-year time series. Okay, so there's basically it's been a very stable place. There's a little bit of trend, and if you analyze it, what it really is as satellite programs come and go over the 20 years, we change our measurement and emphasize maybe later in the afternoon or earlier in the morning to try to match up with the satellite overpasses. And as you do that, you're going to bias the measurements slightly one way or the other. So really the difference between one and this line is mostly due to us changing when we collect data slightly over the period. So there we are. And all the data within a 1 or 3 day lag, we look at every data point, quality control it before we post it. It's openly available at this Coastwatch site. So you can look at NOAA Coastwatch and download any part of the data you want over that whole time series. What's that? Yeah, okay, so a time series. Time series shows you instrument problems, and those just show you funding problems. This was an instrument we had the Moby out there had broken, so we had to retrieve it. We brought it back in. This period was after NOAA had started funding in 2007, but we have to record this. It was a struggle for the program person inside NOAA to keep us getting money, and we were at a low point of money. In fact, we didn't have ship time, so we couldn't bring it out. And Veers was going to get launched here around 2011, 2010, and so our decision was, let's just get everything ready for launch of Veers, and then start spending money again and putting it in for ship time. So that's what this gap is. A couple of other little gaps are something happens to the instrument. I'll show you some pictures later. That it takes us, we only have 2 instruments. If the one at sea fails, we're working trying to get the other one ready in 4 months, so we can't accelerate that too much. So that's where you see little gaps there. That's all from me. But the data, you can get the rest of the data, it's all up in Coastwatch. That's important. It's all openly available. I'm not going to go over this. It's mainly our uncertainty estimates for the instrument for measuring. It's sort of good to know. This is the uncertainties we estimate for the radiance, just the radiance measurement. making the radiance measurement in the lab with the instrument. This is sort of the level of uncertainty we have. It sort of lays out the different parts. We're updating this right now, so this was our estimate. Then when you go to LU, you have other things besides just the calibration of the radiance. Other things fit in there, in situ measurement uncertainty, integration time, a bunch of other parts fit in there. And so you end up with a slightly bigger error estimate, uncertainty estimate for the LU measurement. Then we go and we look at ES, you do the same sort of thing. You have ES in the laboratory, what our estimate is. Then we have to estimate what it is in the field, and see it's a lot bigger in the field. And a lot of that number is right here. And that's in situ measurement uncertainty. The problem there is you have a cosine collector, and it's supposed to be measuring with a cosine response of the atmosphere, which means it's like 1 normalized to 1 here and then starts falling off. If the sun gets like 40 degrees or so, and you have this thing that tilts at all or moves at all, at cosine of, if you just calculate it, if it tilts like 2 degrees, 3 degrees, that's a huge, that becomes a fairly big difference when the sun angle is down at 60 degrees or so. So what you're seeing here is that's really pretty much the cosine problem with this. And so, that's why that increased so much. You go to LW, you've got other things you have to worry about. Your error, your KL, error because of self-shading. This is actually the estimate they had been after correction. I've got a paper that's going to submit within a month, I hope, of the new shading correction. And we'll update this. Basically, so now your errors, even estimate of your errors even bigger for LW, but it's on the order of 2-3%. And then some programs like to use the normalized water leaving gradients. So now you have LW divided by ES. So you have to suck in the ES errors, uncertainties, and now that increases the uncertainties. But it's basically less than 5% at the end is what we think, with as realistic a view as we can. So if you look at Moby, what's worse? We have 3 arms. So you only probably need 2 arms, right? You need an arm at some depth, another arm to get KL, and then you're good. Well, the 3 arms gives us a way to compare the KLs we measure between the different arms. If you have 3 arms, you have 3 different pairs. And so the black here is the top middle, the red is the top bottom, green middle bottom. And you see how well, when things are working well, up until about 575 nanometers, they overlap really, really well. Okay, and this is clear water, so it's homogeneous. We can think of it as homogeneous in the surface. So this is doing really well. But it starts falling apart here. What's going on here? No, we got lots of signal. No, it's pretty broad band. We'll probably have like, okay, I've got, what have I talked about? I talked about radiometric instruments. I had 3 lectures, I can't remember what they were. Radiometric instruments and polarization. That's not polarization. Inelastic scattering. Remember? And I think I said you got to really worry about Raman scattering in above 575 nanometers in clear water. So what you're seeing is you go down in the water. So if you look, the black, it's the top middle. So there's in the upwelling light field, and there you have the least amount of, or the most amount of direct sunlight still. So it's the least effect here, but it's still there. There at the top, the middle, the red is top to bottom, and the green is middle to bottom. And you're seeing the increasing effect of Raman scattering in your KL there. So you're never going to match up here. Well, you will if you use my algorithm that's published to try to correct for this. So you have that. Here's another example of the data set during a recent deployment. And we never got the KLs here to agree well. And so what it told us basically is one of our measurements, one of the arm measurements is suspect in some way. And you might think in this that maybe it's the middle arm, because if you look at the red, the top, bottom, it's sort of in the right range versus this black line, which is the top middle, is almost negative. It might even be negative here. And the green is higher than we expect to have there. And so the black and the green, the common thing between there is the middle measurement. So you get hints that there's something wrong and you need to be careful with the data by looking at having three measurements like that. The other thing nice with three arms is you have a little bit of redundancy. This is what it's supposed to look like in the water. This is the 1 meter arm with the buoy, the top float, and then the central spar. Went out, we noticed that the signal from the top went really small. What happened? Well, we went out and had divers look at it, and where the arm was supposed to be, it no longer is. So basically, a ship probably, yes, came by and got a little too close to the buoy and broke the arm off. If you're in Hawaii, they have these things called FADs. They're fish attracting devices. They're buoys that the fisheries has put in around the island chain, because whenever you put a buoy in the water, it throws stuff on it. Little fish come, and little fish get bigger fish come, and it keeps going up the food chain. So fishermen love these FADs, and this thing's been in the water for 22 years. The fishermen know where it is. So they're always coming out and fishing around it. And so sometimes the guys get too close and something like that happens. So now with this, we still can make measurements, so we still have the bottom and the bottom arm, the middle and the bottom arm. So what's worked at having the three arms has been nice. We've been lucky having a really long-term personnel. A lot of the guys have worked almost since the beginning. The last 22 years, this has been all their work. It's Mark and Stephanie Flora and Mike Kleinholz. There's been some really good people working for a long time. If you talk to Europeans, that's unusual. There, they have these rules about how long you can work on a certain project before they have to get new people coming in. It's like a 3-year turnaround. I don't know how they do it. This has been really important to us. Quality control, Stephanie Flora is the person who does all our data reduction in Los Angeles. She can look at one of these spectra and find a few percent, say there's something going on here, we need to look at it closer. And she'll notice few percent differences in the spectrum. She's 20 years of looking at the same thing. Weather accessibility, it's worked well where we are. We can work a lot of times, which is good because we don't waste ship time. There was some discussion that we should be at the hot site, which is on the outside of the islands. But you talk to the HOTS people, and there's a lot of days they can't work at all. And we have to do more heavy equipment stuff. So we need to calm them. That's worked in collaborating with NIST. It's been really important. So because we've continually gotten to work with really smart people and improve the system. Having extra internal lamps is good. Our pre-post deployment average is about 0.7%, so the instrument's really stable. The region of spectral overlap was really useful. That allowed us to see stray light, allows you to look at checking between the two spectrographs for problems. We're basically pretty much away from casual recreational boating, but not completely. Here's somebody hit it hard enough that they cracked the window in the upwelling radiance sensor. This sort of shows when somebody had hit it. We went out there once and found that, and this line is about that big around polypropylene. Huge piece of line. So we went out there, the divers were out there doing either maintenance or I think it was a maintenance. and came across this in the middle of our tether. Okay, there's a straight, you got the morning bird, you got Moby, and there's a tether line between. It's a continuous tether line. And so they found these knots in the middle of it and trying to figure out what went on, what's going on. Well, somebody went into some of the bars in Maui, I think it was, and started talking to some of the fishermen. And what happened was somebody who was not a very good, nice person came by and went between the mooring and the buoy, and is probably on purpose close to the surface. So they went by between the two, caught it in their propellers. Okay, this is a pretty big line. So they caught it in their propeller and they reached over, and I guess it takes a while, but whatever they did, they reached over and cut the line and then took off. Okay, and so now Moby's floating free. Well, another fisherman was out at the same time, saw what had happened, that had been around, a nice guy, saw what had happened, and came over and towed Moby back into the spot and tied it back on. And we never knew about it, okay, until we went out to look at this. So this is, I think, is a success. We've been out there long enough. The people know about us. They take care of us. When we go out to work on it sometimes, to do the diver cleanings and such, they tie up to Moby with their inflatable. And we've had fishermen come by and yell at us, saying, "Stay away from that. Stay away from that. It's important scientific equipment. Stay away." Okay, cool. All right. So.
I'd like to just comment on how important this is with people who are using the water. So the rural moorings being in perfect hole in Hartsville Sound, which is this part where everything must be rushing fast. But I would kind of meet with the Washington State about what they are looking for, why them, how to do data, how to data and process it. And just developing that we need to literally absolutely that we've never had a problem. Whereas before we had these things that move out of that. So remember that there's people working in your environment and their lives are important in your life. Get something, give them something if you want something.
Yeah, so it's good to have relationships. There was another funny story. Things fail. We've had people cut the lines and we don't know about it, and it never we know about it because we track Argos and it goes out of with the Moby, and it goes out of its watch circle that we expect it to be in. We go, there's alarms that go off at Stephanie's, and I get emails, and we go and track it down and try to find it and tow it back in the spot. A few years ago, one of those alarms went off. And so we were starting to sort of get people together so we could go out in the boat and tow it back. And this fisherman talked to Zhang Ping Li's group, Mass Amherst, I think. He had gone out to go to Moby and make some measurements near Moby. So he had chartered a fishing boat, and the people in the fishing boat emailed him or called his lab and said, "Hey, Moby's not there." And we knew it wasn't there, but he said, "Moby's like nothing's there." And we're like, "What? Nothing is there?" And so we got in communication with the fisherman, and he said, "Yeah, there's nothing there." And he said, "Oh, huh." So now we don't have a mooring and we don't know where Moby is. It turned out that the mooring line for the mooring had broken. And so what we figured out later was a shark or something must have eaten part of it and then it corroded away. And anyway, so we hired this fisherman to basically, he found it and stay by it until we could get out there. We knew then we had to take a bigger ship out because we couldn't just do the one. So yeah, having the relationships is super important. Things we wish we had and we're working on is simultaneous measurements, reduce stray light in the system, because that's an error term in the system. We want better measurements of the compass tilt and roll, so we have a better orientation idea of the instrument. It'd be nice to reduce biofouling This is just, so I'm going to go in, I'm going to transition into what we're doing with the new system, but here's a little bit of deal about system vicarious calibration. I think I said this already, the calibration of the sensor in space. It's important to know it's specific to the atmospheric correction. So if you do a vicarious calibration with one kind of atmospheric correction algorithm, you need to do it again if you have a different atmospheric correction algorithm, because it includes any little errors that might be in your atmospheric correction, and they get sort of canceled out in the process. The data has to be the highest quality you can possibly get, and the aim is to adjust this overall gain factor, which is the G factor, correctly, and that just adjusts the calibration of the ocean color sensor in space. Now, this is from a constant Razan presented Esrin, which is this. Here's a picture of gain factors. This is from Jeremy, one of Jeremy's papers, showing how the gain factor changed over as you increase the sample numbers. So this just shows you need a lot of samples to start converging into one point. This error bars here show you about the uncertainty in calculating that gain factor. Notice 0.995, so that's 0.5%. That's our goal, is to be within 0.5%. So we want to be closer than this. So we want to be out in here. This is not very important other than it's a big number. This is the what we estimate our uncertainty is for the instrument divided by the uncertainty in calculating the gain factor in percent. The important thing here is at the Moby site, this is a pretty big number, which means that the uncertainty in calculating the gain, all these error bars here, is it's basically small relative to the uncertainty that we think the instrument has. What this tells me is that the better that we can make our instrument, the better they're going to be able to do this calibration. Contrast this with another site, and this is because the Moby site is in a really nice, benign, fairly uniform site. The other ocean color validation calibration site is in Busol, which is a really interesting site, has a lot of stuff going on, a lot of spring bloom, a lot of different oceanographic conditions. And theirs, this number is much smaller because the number for calculating the gain is so much bigger. So for them, improving the instrument isn't going to help them too much in the process. For us, the better we make our instrument, the better it's going to be for NASA and everybody. So that's we're working on that now. So in terms of improvements, NOAA is supporting what we call Moby Refresh, basically a new optical system and buoy structure for the Lanai site. NASA is supporting MarrowNet, which is the same new optical systems. The buoy structure, we're matching between the two to support an additional remote site. We're building 3 or 4 of the instruments for NOAA. The idea is if we have that situation where one's broken, we'll always have one ready to go. We can quickly get out. NASA is supporting 2 MarrowNet systems. We designed both systems so they'll match the 350 nanometers of pace, which then makes me always, when I hear Jeremy talk about pace and he talks about, oh, we're going to go to 340 or something, oh no, don't do that. I just got everything down to 350. Every time you go, the other thing that Kurt you mentioned about, going to 300 or whether so it's not having a lot of light, is optical devices, the glasses and everything else gets very, very complicated. And so it was hard for us to get to 350. Getting to 340 means we compromise a whole bunch of other parts with the same optical system. So it gets very difficult going down. So I don't want to see that number change. Structures that allow the optical system to be removed and tapped. We want to, I'll describe that a little bit more in a minute, but it's important. We want to try to do that. Structure that fit into a 40-foot shipping container so you can ship the thing to this site, wherever it's going to be. And then a stability or source monitor, which verifies that the optical system is still the same between when we calibrate it, wherever we are, and where it's going to be deployed. So I'm almost done with all words. I've got more pictures now. So I'm going to go through sort of assembly, the spectrometers we have with our new system. Basically, there's once again a red and a blue spectrometer, and then a splitter housing that splits the light that comes into this piece from the different fibers of the arms and goes to either red or blue spectrometers. The spectrometers, instead of the current system, uses the reflective holographic grating to do the diffraction and change the wavelengths. These things use these inline volume holographs. So basically, there's a gelatin here that they imprint an index refraction gradient in the gelatin, and that gelatin's between two pieces of two pieces of glass. So going through this grading effectively diffracts the light and spreads it out by wavelength. It's very, very stable, and it's got high throughput, and it allows really good imaging through the system, which means that if we have a slit out here or multiple slits out here, we can image them in different spots on the image plane, and you can make multiple measurements at once. And this shows an example of making with the blue spectrograph. This is an LU bottom measurement, LU mid, LU top, the downward irradiance at the bottom, downward irradiance at the mid, down at the top, and the ES sensor. And we've taken this is one image, taken all the data from all the different arms we've got all at once. So with simultaneous measurements, you get a lot of reduction in errors. Basically, we always we're probably not going to do them all at once. We're probably going to take ES and the LUs at the same time, and so that you can sort of keep those normalized together. But anyway, we have the ability to do multiple measurements. We can make 14 different tracks of measurements on the detector with the system. Here's a picture. So I'm going to show you the assembly. So here's the Resnon. The spectrometer we use is the base spectrometer was built by Resnon with the camera from Apogee. Back here is the camera. In here is that inline volume holographic grating. It's all black. Out here is 14 fibers, one that goes to each of the possible channels we can have. So this is the thing we start with. And this sort of shows it again. Here's the spectrograph. Here's the camera. The fibers are off this direction. There's a computer, single board computer in here, power supplies, a radiator, basically fins to dump heat from the CCD camera out here. This is the end cap. When it was assembled a little farther, here's these copper heat tubes, basically to bring heat from the camera up here back to the back fins. There are tubes along with, they're filled with a liquid that even conducts the heat up and down through back more efficiently. So there's one picture as this thing gets brought together. Here's a picture. Back here is the part I just showed you. In the front now, you have those fibers coming out of the spectrometer, and each of them goes to a window back over here. You can maybe see where you are. I can see pretty well. There's a collimator here that takes the light from the fiber, collimates it, so it goes out through these windows, collimated. The next part of the instrument will be stuck up against here and takes the collimated light and does something with it, which I'll show. Basically, it's broken into a bunch of different watertight parts so that if one part floods, the whole system doesn't flood. I'm trying to think as much as we can to keep it as reliable, because this thing could be in the water for 20 years, 30 years, you know. We're putting cases on it. This is a titanium case we have to reduce the corrosion. So this is the titanium case over the front part. Now we've got the titanium case over the back part. This is the instrument as it would be. I think this is the blue spectrometer ready to get mounted. To split the light between the two, the red and the blue spectrometers, we tried several things, and this is what we've come down to. Basically, the light from the outside comes in here, okay, and so this is so this is the light coming from the fiber from the different arm, comes in and gets collimated and then hits this little polka dot mirror. So polka dot mirror is exactly like it sounds like. It's a mirror that has a whole bunch of silver polka dots all over it. So parts of the signal go through the polka dots and go straight through and get recollimated onto the fiber. And then this would say go to the red spectrograph. The other part that hits one of the polka dots that's mirrored will come up here and go off that way and go into the whichever the opposite one or whatever I just said. So one goes in the red, one goes into the blue spectrograph. But this has been our test so far, this has been very good temperatures, had very good temperature stability. The first idea we had were these Fiberoptic Splitters, and those turned out to be horrible in terms of temperatures. We had to redesign everything to match this. So this is a picture of one of the little Fiberoptic Splitters with a scale to show you what it looks like. Here's the splitter housing. So this would come from the different, this would have the 14 or at least 7 ED, LU, etc. fibers coming into it. It get knocked up against here. Those on the other side of this are these splitters on the other this plate. Here's another picture of the splitters. And so in each of the spectrometers, the red spectrometer and the blue spectrometer would be attached. One would be here, and one would be over there. And so everything inside would split and then go around and come back in here. So this is the back side of the splitter housing. So also inside the splitter housing are our internal calibration sources. We have a red, a blue LEDs, and then lamp. They each have shutters, so you can independently turn the lamp on, say, let it stay stable, and all the LEDs stay stable, and just choose which one you want to look at. They go into an integrating sphere, and from, sorry about the noise, I guess I'm getting email. So the integrating spheres, so you have the red and the blue spec with the integrating sphere. There's also a monitor detector, so they have all these calibration sources. Here's what it physically looks like. You have the red and the blue LEDs. They're on a thermal bench to try to maintain its temperature, because LEDs change their spectrum depending on their temperature and also their intensity. There should be an incandescent lamp down in here. Here's your integrating sphere. All this stuff is inside the splitter housing, including a bunch of shutters. And here's some sample data taken with the blue LED and the incandescent lamp, and then the red LED. And this is on the blue spectrograph looking at these sources. Okay, so one interesting thing about fiber optics is, you know how optics transmit the light? Yeah, so basically it bounces off the walls of the fibers as it's going down. And the reason is that at large angles, you're getting total internal reflection. So they're hitting glancing angles going from a high index of refraction medium to a low, and you get this internal reflection. What happens though is that if you start with a certain distribution of rays going through here, they can change if you bend the fiber. Some of them they're called fiber modes. Some of the fiber modes will come in, some of them will go out. What that does is it changes the distribution of the light coming out at the other end of the fiber. So instead of being maybe a nice Gaussian type shape, it could end up with a little bubble somewhere or different intensity. That turns out to be really bad on these polka dot beam splitters, because if you're changing the distribution of light on this polka dot beam splitter on the polka dot mirror, if you move a little intensity, a high intensity point to a different spot than initially was, you're going to change how much gets split one way versus the other. So the way to get around that, we learned, was by using these mandrels, in which you take the input fiber from your collector and wind it really tightly for a bunch of turns around something, and then enter it into our system. And what it does is it mixes up all the modes in the fiber. It makes it so it's a uniform output that's no longer dependent on what it started at. So it took us a bit to figure that out too. So anyway, so here's these mandrels from the input fibers going into that head that gets connected to the splitter housing and then split apart. You guys are getting a whole bunch more pictures than the class, any other class has ever seen, because this is all going on right now. It's much slower than I would like to see, but that's what's happening. So here's the laser. This is the thing I was telling you, it's computer controlled. You say wavelength you want from 200 to 1200 nanometers, something like that. You say I want 340 nanometers, and it calculates and figures out how to move a bunch of crystals inside and how much of this pump laser to use versus that pump laser to use. It's really, really cool. Anyway, so it generates whatever wavelength you want. We use this to do the stray light characterization. We don't have to go to NIST now. Here's an example of some data normalized up here. You can see we're down about 10 minus 4, 10 minus 5 in stray light from there. Here's just the peak blown up. They do this at only wavelengths, and what you want to generate is this, which is something is a stray light correction matrix, which basically tells you if I get light. So this is wavelength and blue spec. This is column number. So if I send in light at this wavelength, say this send a light at this wavelength. Well, let's see. At this wavelength, then it'll be distributed across the array in a certain way. And so with this matrix, we can invert it and get rid of the stray light effect. But to do it, you need a whole bunch of stray light data. So this is the example of the blue spectrograph, all sorts of different spectral lines, so we can sort of characterize the stray light as a function across the array. Sort of interesting is we actually start a little bit below 350. So say 340 is showing up here, 340 nanometers. And you see it shows up over here too. And so this array is only in pixels, but it's, if you do a spectral calibration, it's like 340 to 700 nanometers across there. You remember diffraction gratings and diffraction in general. You can have first order diffraction, second order diffraction, third, etc. What this is basically second order diffraction from the light out there. Okay. If you remember the equation for that, I said this is just pictures, but the equation for that is d, the distance between the diffraction slits, say. Sine of the angle that it comes off at is equal to m lambda times the rate of m sort of order. So if this one should show up at twice the angle that this one showed up, oh, this should be theta 1, sorry. And it's not quite, because the spectral calibration on where it shows up in the array is different for second order versus first order. But it's pretty close. And so it's sort of cool that you get the physics showing up there. Okay, and here's the same thing for the red spectrograph. You notice there's a little, the other ones are nice and symmetric. This has a little shoulder in a lot of the lines down here. And we're afraid that that's actually part of the lasers and not part of the system we're trying to measure. So we're gonna have to figure out how to deal with that and develop a stray light matrix. We ran into a lot of problems that stopped us for a while. Fluorescing, the laser light comes into an integrating sphere, and we sampled that. And the spectral arm was fluorescing a lot and causing a broadband thing that looked like stray light, but it turned out we did a whole bunch of tests and figured out it was the spectral arm. So we had to figure out how to illuminate the detectors uniformly enough that we could get away without us integrating sphere. So we're doing that now to try to simplify. But it is something to remember if you're using spectral arm, that it will fluoresce if it's not perfectly clean. We have stray light spectrally. We also have stray light moving from one track to another. And this is the matrix that we came up with for correcting that. At sea, you can do this pretty easily by just making measurement with one wavelength, one track open, and seeing how it comes onto the other tracks. So we developed this matrix with some data from at sea. The way you look at this is sort of an example of a corrected, which is the green line versus uncorrected. These are like in counts for the off diagonal elements are in counts from like -1 to 2, somewhere in that range in counts. The on diagonal element is like, this is saying if I illuminate track 2 with this much light, obviously an ES measurement, then this red amount of light shows up in the other tracks, and after correction, I bring it down to 0. So this sort of shows that even with illumination on the order of 10,000 counts here, we can correct it to basically 0 for the other ones. So there's ways to get rid of this, but it is something you have to take into account when you're trying to do simultaneous measurements. Wavelength calibration is done by looking with a gas penlight lamp. This shows mercury argon lamp and this different spectral lines. You know where these spectral lines are really accurately, so you can change the pixel location to a wavelength and use the calibration for that. Here's a neon lamp. Thermal characterization, we have this big instrument. So we had to, this is sort of, by the time we're done, this was the prototype. To do a thermal characterization, we somehow have to bring it up into the same temperature regime. It's huge, so we built its own little hot tub. And so here's the hot tub, we drop it in there, the fiber comes out and goes into a source, a uniform source and constant source. This is all the plumbing to change the temperature inside the hot tub. So we have to do this thermal characterization for the instrument. There were some interesting results, but more details than you want. Stability source and monitor, here we are. To be able to do the remote, the measurement in a remote site, we need to have some way to maintain our calibration. So we're using, right now, we're using this CAS radiometer as a monitor, a radiometry monitor of this source. We have this source that's a leftover from the Symbio Seawith era. It's called an SP satellite quality monitor. We bought one, and right now it's working really well. It's just heavy. It's about that long. It weighs a ton. It takes 2 people to carry it. So we'd like to figure out something better. But right now, this is working pretty well. Sort of another funny story along this line. I heard an interchange between Colin and someone talking about outfitting their lab and buying things for their labs, and you can look on different places. Okay, well, we got funded. We're going to buy one of these SQMs. The company was having a hard time giving me a quote and coming through with something. We looked on eBay. We found one. There's only 2 of these made. One, the company still had. The second was NASA property. So we went to the person, you're interested in selling this? Can you tell me something about it? It disappeared. No longer was up there on the site. Obviously, it should not have been for sale on eBay or Craigslist. So be careful when you're buying things. Find out where it's from. Yeah, I don't know why it showed up and where it went. Anyway, so yeah, so this is what we're using for a stability source and a monitor. The new system, this is a picture of biofouling. In the window, you have to, if you can have the deployment in between the driver cleanings, you want to avoid this as much as you can. Here's just shows from the outside. We have a copper tube that goes over the LU collector, so it extends down. So that stops most of it, but occasionally you get something like this. On the outside, you could get barnacles. The bad part is if some barnacle figures out how to grow on copper and goes on the inside, which has happened, which is like, really? You can grow on straight copper? But anyway, occasionally that happens, and we have to get it clean. We're going to add a UV LED lamp at 285 nanometers, and that'll cut down a lot of biofouling. We hope. So we're working on that for the new system too. That'll be in it. Biofouling may be able to stop that other stuff. It's going to have a hard time stopping these guys. Every once in a while, we'll get a signal that's sort of really strongly varying, like it's blocked completely and it's okay, and it's blocked completely and it's okay. We sent a diver out to check what was going on. He unscrewed this copper thing at the end, and he gets to the end and pulls the tube off, and this guy jumps out. Scared the crap out of the guy diving. I'm glad he didn't drop our anti-fouling tube. But anyway, it won't stop him, although it will probably make him blind if he's inside that goes in there. It's got all this 285 nanometer light. The plan now is to put the new instrument here. This is the original Moby site. We've got permission to put another site, another mooring here. In fact, we've put the mooring in. I was hoping I could show you a whole bunch of measurements from the instrument, from that full system here at this point. Now it's looking like beginning of September for a bunch of various reasons that we'll get to put it there. And was there anything else important here? It's on a sort of more sloping site than our original one, so we have a special anchor for it and such. But anyways, what the idea is, we're going to have between Moby Refresh and Maronet, we're going to have a year of data between that Moby and the new systems are collecting at this other site. And so we can do a crossover between the two instruments. We got a 22-year time series. You don't want to throw it away and start over. So we have to validate that the new instrument is working as well as the old one, and it's giving good measurements. And then we will move the Mero Refresh and get rid of the old mooring. I'm sorry, not get rid of the old mooring, keep the mooring, but get rid of the old system and move to the new system. I didn't talk about the structure too much. I couldn't find any good pictures of the new structure in Hawaii all constructed. This is when they were building it in Rhode Island. Do you mind those little stories, sidelight stories? Are those okay? Okay. NASA's big into, when they do all of our systems, pretty much, they start from little commercial parts, but we build them into this system. So it's pretty much one-off stuff, a lot of it. But they're really big into what's it, COTS, commercial off-the-shelf instrumentation. And they really will push, you want commercial off-the-shelf. But you're not going to build if we get 5 of these or 6 of these in the world, that's pretty good. And they're actually making a couple more in Europe that we're talking to Europeans. There's not a commercial market for this. So it's hard to do things. But I thought, okay, we have to build a spar. We wanted to do carbon fiber spar. I will, to try to make it as much commercially available as we can, I'll find a company that does these sorts of things. So I went to Hall Spars. Hall Spars was famous in the sailing world, which is where I live as much as I can. When I'm not skiing, I guess. So the sailing world, Hall Spars, sort of the leader in carbon fiber masts and all this stuff. So I go and we get Hall Spars to build our systems for us, this structure. Great, I've got this company that's been around forever, doing it really well. If you're familiar with the sailing world, Hall Spars went bankrupt. Just about the same time they finished these things, they went bankrupt, which meant, and they lost the manual. We lost, between the time I read the sailing world and found out they were bankrupt, and we got in touch with them, they had lost the manuals, the things you build these things around the forms. So the company we have to do to buy the next 4 of these things is having to start over from scratch. You think you pick a big company like that, it would be really good, but this didn't work out very well. But anyway, here's a picture of it in Hall Spars of the carbon fiber structure from Maronet. Here's with the collector attached to the back arm. We can pull the collectors off here. There's a channel on the base of the arm. You can sort of see the channel here that allows us to pull the collectors off with the fibers still attached, take it all the way off the buoy. So the idea is the whole optical system, wherever its remote site is, you can disassemble the optical system from the rest of the buoy without taking it apart. So maintain the calibration part and ship that back to Hawaii, so we have a common calibration between Moby Refresh and Maronet, wherever it is. So that's sort of the special part of this. Carbon fiber is a little stiffer too. The guys who at Paul Suarez don't understand that we want to measure the upwelling radiance and not the downwelling radiance. So this is upside down. It doesn't matter. It sort of shows you what's going on. Here's a picture again of the stability sources we're going to be using. We've tested the blue spectrometer a lot at sea by putting it alongside the Moby buoy at the bottom and making measurements simultaneous. The system is stable, and we can look at Fraunhofer lines. We have such high resolution that we can measure the spectral calibration with the Fraunhofer lines, and it shifted less than 1/10 of a nanometer over a 4-month deployment, which is good. The tracks, each of those tracks were very stable over deployment. So we've been able to test a lot of stability. Here's comparison between the Heritage and the other. This is the water leaving radiance, and between Moby is the M and the new system is R. It works well. Here's ES. The scheme that we have for Maronet is taking another site that has enough logistical support that we will do it. Right now, we're aimed for Perth, Australia, because David Antoine lives in Perth, Australia, and David Antoine runs the Busseau site in the Mediterranean. So we know that he knows what he's doing. So he's at Curtin. He's at Curtin University in Perth. So now he was in Bill Palm. But anyway, so he's in Perth. He's working with us. We'll deploy it there. It looks like we have 2 Moby structures that will be at that site. That allows you to go out on one cruise and deploy a new one and take back the old one, versus if you had just one structure, you'd have to go back and forth. The optics, when one instrument is in the field with this optics, the other one will be sent back to Hawaii for calibration with that source and monitor. So we can, that's why originally it's well, Maronet, that's where the net came from, it's Netflix, because you're always going to be having something going back and forth between the 2 places. Data forwarded to a central location, so it'll be commonly processed in Moby, so we'll use the same system to do the processing. So that'll be as consistent between the 2 sites as you can. The other thing about Perth, it's in the southern hemisphere. Moby, being in the northern hemisphere in Hawaii area, has a real problem with sun glint with a non-tilting instrument in the summer. And same thing would be in Perth in its summer, but they're opposite. So we will have a complementary station. You have a central calibration and characterization site. These things were required by the In-Situ OCR white paper that was developed by the Ocean. I ought to stop now. I'm losing all the international IOCCG, International Ocean Color Coordinating. Okay. So basically, I'm done now. Vicarious calibration site since '97. We got this long time series. It's been thankful to the guys at Moss Landing, NIST, and NOAA that it kept going for so long and kept the standards really high. And just as importantly is this bottom part, is if you're going to have a time series like this or any support like that with these guys who are working in the field for the most part, you need a lot of dedicated people inside the agencies to help you out. People like Paula from Tempe, Kent Hughes at NOAA, and all the people that help you keep your paperwork flowing, keep your money coming, because it's not cheap. We have 5 or 6 people in Hawaii that work with the project. They're people, they really work for San Jose State, but they're living in Hawaii because it's easier. And 2 people in California, and then myself, which I'm a little teeny part of this whole thing. And then I got a friend, Garth Leeson, who works with me in Miami, but we're also just part-time on this. And just part. These other guys spend all the day, all the time doing it. But it takes a lot of work inside the agencies to help us with a lot of funding. So we're really grateful for that. Yes.
Is Moby the only system that provides Spectrograph calibration to their aerodynamic.
So, yeah, so it's not the only one. Maris used Busol also, this Mediterranean site that they runs. There's the Aeronet OC sites. Those, if you talk to Giuseppe Zagordi, who sort of developed those things, that is not really to an ocean, to vicarious calibration quality. It's good, and it's good validation. It's important validation data and stuff like that, but they're not they're not to the quality that we're doing here. What's that?
What are they?
No, they're used for validation. And maybe the thing in my view, my very parochial view, I'm sure, and anybody else can give a different view. My view is that you need the most accurate measurements you can have at one spot, and then do your calibration there. And it has to be the best spot you have, the best measurements you possibly can make. And that's what Moby tries to do. Once you have your calibration decided there, if you look in say the OC, the Aeronet OC site that I'm familiar with, that work with the NOAA group a lot, is one in Long Island Sound, one's in I think there's one in off of Woods Hole, yeah, what that's called. What's that? Yeah, okay, MVCO, Martha's Vineyard, yeah. So you have Martha's Vineyard one, there's one that's run in the Gulf of Mexico, there's one that's run on the, in Southern California off Santa Barbara. Those are the ones, the primary ones that are working with NOAA right now. There's to do Aeronet OC, you have to be on a platform, so which means you're in relatively shallow water, although the water can be optically deep because it's pretty ugly water. You're in coastal environment, so you're probably not as homogeneous. You could be in like the Long Island one. It's very stressful for atmospheric correction. Long Island. So you need one place to say that this is the calibration. We think this is the best calibration of the sensor with the least stress in the atmospheric correction you can have. And then all these other ones to check the validation, because that atmospheric correction might not be working at this place or that place. And so you validate that your atmospheric correction, you're getting good LW measurements from the other places. And so by having all of those sensors around, you get really good validation that your measurements are working well in places. If they work well in Moby and they don't work there, then it's probably your atmospheric correction has got some issue and you need to work a little harder at that. There's a couple other things happening too.
And I just think it's really important to confusion for a lot of people, the difference between calibration and calibration situation. You're trying to calibrate a satellite, something on satellite. That high calibration is broken up. The lots that happen to that sensor on its launch and on its work. And so what NASA is trying to do is figure out how the sensors, the radiometers on the satellite are changing over time. And that's the purpose of Moby, is to look at these changes in gain or whatever. And those are really nitpicky processes that has to happen, but it's to tell you that the radiation measurement is raising the absolute term. And so that's what we consider to be one site. And you want to pick that site that just doesn't have any other, the least number of other variables. So the clearest water, clearest atmosphere, farthest away from aerosols, just you want to move all of that so that you're only looking at the difference between what radius is detected and what radius is not. And so it's not to say that having other boring or other elements is not useful, but it's not useful for figuring out what is happening to the sensor. So just keep in mind, very, very clear the difference between calibrating a satellite-based sensor over time compared to the atmospheric pressure work well beyond that. And so just create really different systems.
Yeah, you need to, So every Thursday evening, we have our telecon of talking to each other, making sure the whole group gets input and figured out. So you need some group in the world, I think, looking at ocean color measurements that'll spend 2 hours talking about a 0.1% problem with the data and what are we doing wrong, where are our issues here, what's happening. So you need somebody working really hard at the most accurate things you can. Everybody shouldn't be playing with spinning their wheels this way, but somebody has to be, and worrying about it constantly. So, and that's what we do.
Because that kind of detail might be tedious to do, but you need someone to do that for you so that when you can apply algorithms to what you call a data set, you get some math. So it requires this really intense attention to detail. And that is taken away because if you get crappy data coming from the side, then everything comes through that.
Yeah, Kurt talked about looking in your algorithms and finding some problem with it. You want to talk about a bunch of paranoid people. Is if we're doing it wrong, and it's a constant nightmare. If we're doing something wrong, it turns out something in Moby has been off for a long time. I hate a lot of people be pretty pissed. Yeah. Anyway, so there I am. I think that's. Oh no. Following Kurt's lead, this is what I hope. So this is my boat that's in Booth Bay Harbor. Hopefully, maybe next week it'll be off here, anchored. If you've never seen, so I keep the boat in my backyard up here. So you get a keel boat, fairly 35-foot keel boat, full keel, heavy boat, in your backyard. And you hire this guy with a truck who comes into your backyard with a hydraulic trailer, lifts it off the stands, brings it down to a normal boat ramp. We had a crane, we put the mast up with the crane, but he brings it down to a normal boat ramp and just drops you in the water off the normal boat ramp. Before we started trying to do this, I'd never imagined from Seattle or in Florida, no way. But in Seattle, even growing up, I never heard of anything like this going on. But in Booth Bay, lots of people in Maine, lots of people keep their boats in their backyard, and they hire these guys that allow the trailer disconnects from the truck and is cable down and allows you to float the boat right off a regular boat ramp. It's pretty neat. So there's the boat.
So growing up, I've never seen anything about this. I'm curious as to what the alternative is.
In Seattle area, travel lifts. I mean, you've seen travel lifts, right? Travel lifts are like, so you have the boat in stands in a boatyard, and the travel lift is like 4 wheels on a big legs, and it has the bridles, and so it'll go over the boat, take the boat up with the bridles. And then it's got a front part that opens to allow you to get over the boat. And then you have the bridles and that lift the boat up. And then you go into some part of the boatyard that has a cutout on the dock and you drop it in like that. So that's sort of more normal around the world, I think, when you don't have such nice tides and steep boat ramps. Yeah, Florida, that's the only way you do it. There's no way you get tidal to it. I was impressed with it.
I think we should get the
Yeah, we thought about going at least to Marlins in Nova Scotia, but I like going around where there's bays. You always see land. Anyway, so all right.
1 o'clock again.